So, very good afternoon to one and all. Uh, welcome all the students on this live interactive session on NPTEL online certification course on mass transfer operations 1. So, we are in the week 11 and 2 weeks are left. Week 11 and I think only 1 week is left until this course gets over. So, it's time to like buckle up all the contents what have been gone through. So week 11 and week 12 will be much more focused predominantly on the distillation, that is module 5 and 6 itself. So what we'll go is just some more methods for the identifying the number of the idle stages required for the separation of the gas and the liquid in the distillation column. So what we have gone through till now is for like Maccabi-Thiele method, but now what we are going to do is for like some of the methods called the Ponchon's favorite method also. So before just proceed, warm welcome to all the students, and this is the course that has been offered by Professor Vishnupana Mandal, who is a professor in the Department of Chemical Engineering at Indian Institute of Technology, Madras. A little bit about myself is that I am Rajput Shubham Kumar, and like I'm taking all the live interactive sessions for the Mass Transfer Operation 1 course on NPTEL, and I'm a PMS scholar in the Department of Chemical Engineering at IIT Madras. So let's begin with the week 11th. So this is the week 11th of the course. Already we have gone through week 10 courses. We have done we started from like the basics of the mass transfer, loss of mass transfer, various operations in the mass transfer, and then we came down to the distillations column and designing our distillation columns and the various operations to be carried out in the distillation columns. So week 11 is the content for the week 11 is much more like the multi-stage batch distillation with the reflux. So what we've gone till week 10 is based on the batch distillation or the steam distillation as well as the Maccabi-Thiele method in order to identify the number of the theoretical stages for the gas liquid separation. And we have also seen the rectifying in the stripping section and the concepts of the operating line for the rectifying of the stripping section in terms of by solving the numericals. So we solved the numericals for all these cases in the previous live interactive sessions involving the Maccabi-Thiele method, operating line, equilibrium line, and how to draw the plot, how to determine the number of the stages using the graph papers, and that all we have already done. So this week 11 is based on much more, instead of batch distillation, we are much more focused on the multi-stage batch distillation with the reflux. And the second point is the Ponchon's favorite method. So this is another method in order to identify the number of the theoretical stages in the distillation column. So we'll begin with the multi-stage batch distillation with reflux. So I will write up now. Multi-stage batch distillation with reflux. Okay, so in single stage batch distillation, that is also known as a daily distillation, the purity of the product is practically governed by the concentration of the feed and the fraction of distilled out. However, in the multi-stage distillation with the reflux, a significant higher product purities as well as the higher fractional recovery of the product can be achieved. So I can say that the difference between the batch or batch multi-stage batch. So purity of the product is governed by, the first one is concentration of the feed, the second one is fraction distilled out. Whereas for the multi-stage batch distillation, what you can see, the higher purity product as well as the higher fraction recovery of the product can be achieved. So because there is a multiple stages, higher product purity as well as higher fractional recovery of the product can be achieved. Okay, so these two are the main difference between a multi-stage batch distillation with reflux and a single distillation column. So what you can say is that if I draw a batch distillation column, it has a pot, there will be some steam flowing, steam, and this will coming out the condensate, and there will be a column on the top of this. There are multiple stages. Suppose you can consider there are multiple stages. I will take the vapor, pass it to a condenser, and the reflux I will collect into a reflux pot. Half of will be refluxed, and the rest will be collect as a condensate. So what we call as a distillate, and as a reflux. So in the theoretical analysis given below, we assume that the constant molar overflow occurs, that is the vapor rate G and the liquid rate N remains constant in the column. Okay, and the liquid holdup on the plates is negligible. However, the batch distillation is an unsteady state process. So if you like and say in the last classes also that batch distillation is considered as an unsteady state process. However, we assume that the pseudo steady state condition avails because of the contact of a gas in the liquid. This means that the liquid and the vapor concentration profiles in the column at any moment are same, and as a steady state profiles achievable under identical conditions. So it is easy to understand that if the reflux ratio is held constant, the distillate concentration will decrease as the distillation proceeds. So the column may be operated till the distillate quality remains within the acceptable limit. So this is what we call as the batch distillation. Whereas case of the constant reflux in terms of the multi-stage batch distillation, so this the distillate concentration remains constant. It is less than a constant reflux ratio or constant reflux operation. Alternatively, the reflux ratios continuously increase so that the product concentration remains constant for some time. This is called a variable reflux. So if the distillate concentration is fixed, we can say that the reflux ratio is constant. Another term is known as the variable reflux operation. So there are two terms of reflux like we talk. First one is constant reflux, and the second one is variable reflux. Okay, so in general practice, the constant reflux operation is more common in term as far as the variable reflux ratio is concerned. So in order to use the Rayleigh equation when a column is refluxed, generally one or more iterative calculations are required. Typically, a Macabre-Thiele diagram is used to obtain the information needed in the calculation what we have already been discussed. So, so this is what we have discussed related to the Macabre-Thiele diagram, and we have also to know the equations like somewhat. I will type generally the equation ln of w by, so if we take I have equation w I dx w x t minus x w. So this type of equation we have already seen, and this is somewhat related to the for the batch distillation columns. So right now what we are going to do is to see some of the terms related to the what you call as a Ponchon severity method. But before proceeding to the Ponchon severity method, we will solve one numerical problem on the basis of that. So like there are derivations for the variable reflux operations also, but I'm not going to the derivations. What we'll do, we will directly take a numerical and we'll try to solve out the points on the basis of that. So first we will see what is given in the question actually. So if you see, the question has been saying that a 100 kilomole mixture of 50 mole percent A and 50% B is subjected to a batch distillation column at 1 atmosphere total pressure. The column has 3 trays, a steel pot and a total condenser, and the top product contains 96 mole percent of the A. Concentration of A is already provided in the top product, so the bottom product will contain 4% of the A and the rest is the residue. The final concentration of residue is 4%, that is what we discussed. So the reflux is saturated liquid, so the slope of the Q line will be 1, that is Q equal to 1 for the saturated liquid. Calculate the composition and the amount of the distillate. So we have been given with equilibrium data also with that, so we'll start processing with the data what had been given to us. So if you can see, if you carry out the total material balance equal to D plus W, equal to D plus W. So feed is given as 100 kilomole of mixture is equal to distillate and residue we don't know. Now what we do is that the component balance of A we have. Since the concentration of the A in the top product is given as 96%. So the component balance of A, therefore F into ZF, D into XT, W into XW. Therefore 100, F is 50 mole percent of A in the field equal to D into concentration in the feed is 0.96 plus W into concentration in the residue is 4% is 0.04. Therefore 50 equal to 0.96 D plus 0.04 W. Now we know that since F equal to D plus W and 100 equal to D plus W, so we can write W as 100 minus D. So we write the same thing here. In the previous equation we replace W by 100 minus D. Therefore 50 is equal to 0.96 D plus 0.04 100 minus D. So we will try to solve out this equation. Further simplifying, you will try to get the answer as follows. So after solving this, you will get DS 46 by 50 minus 4 will be 46. Divided by 0.92, because this 0.96 minus 0.04 is 0.92. This turns out to be 50 kilomole. So D is 50 kilomole, W will be, therefore W is equal to 100 minus D equal to 100 minus 50. That turns out to be 50 kilomole of the residue, and 50 kilomole means the rate of residue and the distillate are the same. Now what we'll do is that this is a case of an operating a batch steel with a variable reflux ratio what I have given in the question. So the concentration of the more volatile, that is NXN, if you see the question, that the concentration of the more volatile NXN is still decreasing gradually, but the reflux ratio has to increase continuously until the bottom liquid concentration drops down to the 4% of NXN. So 5 ideal trays from plate to a reboiler are fitted between the operating line and which, and the overall vapor concentration should be 96% of NXN. So what we'll do is that we have to try to plot a diagram here. So the steps will be, so if you take the equilibrium, the points like X and Y has been given to us already. So both of them varies from 0 to 1. and the data has been already been given to us in the question, that is this point. So this is the equilibrium data that has been given to us, and then we have to plot the same thing in the plots. So what you have to do, you have to take a graph paper, you have to plot y-axis here, x-axis here. This will be a 49-degree line, and if you plot and y equilibrium plot, it will somewhat come like this. Now since the xd means the distillate is given to us xt comma xt, that is 0.96, 96% of it, so 0.96, 0.96, and xw is 4%, so 0.04, 0.04, 0.04, and feed means zf comma zf is given to us 0.5, 0.5. Okay, so what you have to do, you have to look at all the points. Suppose if xd is here, xw is here, and zf is here, so you have to draw a number of the ideal stages. So you have to plot it from like such a point. You have to take a point here, go straight, come here down, then again go straight, come down, again go straight, come down. So here I'm just drawing it like randomly, but if you plot in the graph, you have to determine the number of the theoretical ideal stages required for the separation. So if you draw, you will get a fine number of plates as 5 and a reboiler. So it requires a 5 ideal trace if you draw it properly. Okay, so this is how you can draw. So another thing, what I have been given calculate amount of the top and the bottom product, that is already we have calculated what initial and final reflux ratio should be used. So we have mentioned that to determine the total moles of vapor to be generated to achieve the separation. So we'll be drawing a bunch of the operating lines originating from 0.96, 0.96 and having a varying slopes, and we'll see which one fits. So like 0.96, 0.96, this is, so this one, sorry. Sorry guys, I think so X day, this is 0.96, 0.96. Sorry, there is a problem with my pad. I'll just write it down here. This is xt, and this will be 0.96, 0.96. I will be drawing an operating line straight away from here, cutting the point zf. Suppose this goes like this. This will be the slope actually. So in each case is the fit for ideal stages between the operating line and equilibrium curve and determine the bottom concentration, that is xw. So what you have to do is to determine the different types of operating lines and determine and fit the equilibrium and operating line and find the bottom concentration, that is xw. Using the data of xw and xw as well as the slopes of the bunch of the operating lines that I have drawn one here. So this is one of the operating line. In the plot, you can determine specifically the data. So by drawing a bunch of the operating lines, draw and evaluate the integral of the following equation in either numerically or graphically to get the total number of moles of vapor generated. So what you have to do is to use this equation and determine the, so this is like this is much more tricky equation. So this equation is w minus the xt minus xwi. If I take this I, integration dx w xt minus xw whole square minus dl by dg. So this is an equation you have to use for determining. So there will be different parameters that will be given to you. Suppose dl by dg equal to L by G, and this has been xw determined, and 1 divided by xd minus xw whole square 1 minus L by T. So these three parameters you have to determine and you have to plot. So we will be getting like these different parameters. Suppose for like 0.417 you will get xw as 0.5 and this one is 8.106. So after solving this numerical, solving this equation using the above parameter values, you will determine the same. Suppose another value, I will just write it out. So these values are I'm getting from the after solving the above equation. Okay. So what you have to do using the XD and XW data. Okay. So using the XD and XW data from the plots and using the slopes of the bunch of the operating line drawn, evaluate the integral of the following equation. So we have to evaluate the integral of the following equation either numerically or graphically to get the total number of moles of vapor generated during the distillation. So this is what you have to do here. And after this, the total number of moles of vapor. So after determining the integral of that above equation, total mole of vapor will be given as 100 into that is 0.96% minus 0.5. Suppose I am solving for the first one is 138. Okay, so I'm taking this one actually, the first one at the SW is 0.5 and I'm determining the number of the. So the 0.96 is the fraction concentration of the component A in the distillate. And 100 is the total mole of flow rate, that is 100 kmol per hour. So there will be like so the three things that I have taken here is by plotting the area under the curve. So the area under the curve will be you can obtain after solving that equation. So that equation y-axis will come like 1 divided by xt minus xw whole square 1 minus dl by dg. So this is x-axis. So sorry, y-axis, and the x-axis will be xw. So if you plot by taking all the data, there will be like multiple points, and you have got like it. So what you determine is to take this point, the frontage, and then and to determine the area under the curve. So if you take the area under the curve, so area under the curve will be 3. So this is what I have taken up here, area under the curve. Okay. So this is like a tricky numerical because there is much more to learn, but this kind of questions can be asked, cannot be asked in the final examinations because it requires much more in-depth knowledge of all the cases. But what I will say is that it's better to go through each and everything. Uh, okay. Now another thing that we'll discuss is the like another section of the of this thing. So what we have discussed till now is this numerical and the multi-stage batch distillation along with the reflux. And there's another thing that we wanted to discuss is the Poisson severity method. So this thing, I think you must have gone through all the lecture notes already, because if I go through all the derivations again and again, it will make much more complex for you guys. So what I will do, I'll just say a little bit about it, what is Poisson severity method. Okay, so This method is known as Ponchon-Savarit method because it was developed by the Ponchon and separate independently, and variations in the internal vapor and the liquid flow inside the distillation column depends upon the enthalpies of the mixture. That is what they have considered in this method. So the equimolar overflow assumes that the rates are independent of the energy balance, and to remove the assumption we must consider the enthalpy balance explicitly. So the main thing is that variation in internal vapor and liquid flows inside a distillation column depend on the enthalpies of the mixture. And the second thing is that equimolar overflow assume assume the rates are independent of the energy balances. So it is a more rigorous method and it's free from the assumption of constant mode overflow. So this one is another one thing. It is more rigorous compared to the mecabethylene. Free from the assumption of constant molar overflow what we have considered in the mecabethylene method. So in order to use this method, it is suggested that the enthalpy of the steam appreciably depends upon its composition. So this Ponchon-Savarit method is also a graphical method of is a graphical method similar to the mecabethylene method of the material and energy balance equations as well as the equilibrium relation taken together. So I think I will show you through a distillation columns like we already have, like consider this as a distillation column. There will be a feed point and determine this will be a rectifying section, this will be a sorry stripping section. There will be a condenser to accumulate into a condensate drum. Half will be reflux and half will connect as a distillate. Similarly here there will be a reboiler, half will be turns at a vapor and this will be a have concentration and so if you consider the rectifying section, consider the material and energy balance taking over the thing. So the total material balance for the rectifying section I'm just writing out the basic equations for the gas and the liquid. And that is, if you consider the tray, the NH tray, gas will be Gn plus 1 equal to Ln plus D. So this is equation 1. And the component balance, if you can write, you can take the component A Therefore, Gn plus 1 yn plus 1 equal to ln, that is liquid crystal concentration, plus d into xt. And if you write the energy balance for the same, so what we have is that, because we are considering going energy enthalpies also, so we are to write the energy balance for the same. Earlier we have been writing only the component balance and the molar material balance for the component in terms of mechabethyl matter. But for constant stability matter, we are going to consider the energy enthalpies also. We have to write the energy balance for A. So if you write the Gn plus 1 if I say energy is E, EI n plus 1 equal to ln I n plus d dt plus qc. Okay, now what I'm not going to like derive all the equations, but I will write the in general equation what we have after coding up and ended. So we already have Gn plus 1 equal to ln plus t, and we have the component balance Gn plus 1 yn plus 1 equal to ln xn dxt. Therefore what we will do is that Gn plus 1 yn plus 1 ln xn. I'm just rearranging the terms so that we can simplify this form. It should give out to be ln upon Gn plus 1 equal to xn minus yn plus 1 upon xt minus xn. Okay, so it's better to see the equations, and we assume that the reflux may be a subcooled liquid for the rectifying and the stripping side. For the rectifying section, we assume that the reflux is a subcooled liquid, and that is a liquid at its bubble point. And in general, the xd is a mole fraction of the mole time in it. So similarly, you can draw out the material balance for the component xd, and also you can determine the energy balance for the stripping section also. But still, I think instead of going to the deeper points again and again, it's better you guys can go through the engineering balances. So what I think I should discuss is that what are the plots that need to be converted. So in constant solvent method, the liquid and the vapor concentration curves that XHL and YHG are plotted. So how these plots are plotted is that we will be having a graph paper. We will plot X and Y, and we will be having the enthalpies of the liquid and the enthalpy of the gas, and there will be like two different curves coming from like this for these things, and there will like the different lines connected. So these are the operating lines, and one will be this. Suppose this is HGY for the gas and HLX. So these two are the enthalpy concentration curves. So the point on this diagram represents the composition of the enthalpy of a phase, that is either liquid, vapor, or a mixture of liquid and vapor. We denote that this point by a term, and that also represents the flow of a particular phase. So this is how this functions. I think it's much more complex compared to the Mecca-Thile method, but it's much more giving it a try once, because here we do not consider the constant molar outflow, but we have considered the energy balances, because here we are considering the enthalpies for both the phases as well as a mixture of A and B. So apart from this, what numericals, I think numericals we'll discuss it at a later point in the next class. So we'll solve some of the MCQs related to the that for what we have discussed till now. So if you see, some of the numericals has already been asked in the assignments problem also. So today we'll try to solve out some of the so using a numerical based on this multi-stage batch distillation with reflux, and we have seen some part of this constant solvent method and why it's been considered apart from the Mecca-Thile. In terms of numerical for the constant solvent, we'll discuss for the next week. But for this week, what we'll do is that we will just look for the MCQs as well as some sort of numericals. So right now we're going to discuss the numericals for this week on the content lectures. So the first one we'll discuss right now. So what we'll do, we'll discuss the first one. In multi-stage batch distillation, constant reflux, as the distillation proceeds, distillation concentration will. So you discussed the concept of multi-stage distillation and the batch distillation. So the first one relates to the multi-stage batch distillation, what the first topic that we discussed when we started this live interaction for today. So in multi-stage batch distillation, that is not a unsteady, it's a steady state process in which the distillation has been conducted continuously. So it's a steady state. It remains steady with respect to the time. So in multi-state distillation with constant reflux, as the distillation proceeds, distillation concentration will increase, decrease, remain constant. So with constant reflux, as the distillation process, distillation concentration will decrease or increase. So I will say that distillation proceed, distillation concentration will decrease. So now why decrease? I think it should remain constant, right? But the actual thing is that at the starting point of the distillation, it will take some point of time for the distillate to reach at a one particular concentration that will be a constant value. And as soon as your feed has been continuously pumping at a constant rate, the amount of the distillate concentration will remain constant, but it will decrease because the amount of the rectifying and the stripping section will have to separate the gas and the liquid again and again. And because it's a steady state process, it's a steady state process. What we have to do is that the trace, the amount of impurities on the trace, as well as there are very more terms that we already discussed, like weeping, coning, dumping, flooding will happen at some point of time that will reduce the concentration of the distillate. So in multi-step distillation, which is steady state, not like batch distillation, which is unsteady state. So in multi-step distillation, it will operate for a longer period of time, and as the time proceeds, the concentration of distillate will decrease because of the various impurities, as well as the various detrimental operations that is happening inside the distillation columns, like the coning, weeping, dumping, flooding, and so many terms that we already discussed. So the correct answer for the multi-stage batch distillation with constant flux is that its distillate concentration will decrease as the distillation process. So you should remember this point, because some of you will say it's a constant flux. That is not constant flux. The concentration of the distillate will be constant, but that's not the case actually. It should decrease, and it will definitely decrease because of the various detrimental problems inside the column. Okay. So we'll go to the second one. In multi-state batch distillation with variable reflux. Now this is like variable reflux. We'll discuss two types of refluxes in today's lecture. That is, one is constant, and the second one is variable. So in multi-state batch distillation with variable reflux, reflux ratio is continuously increased so that the product concentration. Yeah, so this is like the similar term what we are discussing from the point, but it is like in another way. So in the same multi-stage batch distillation with variable reflux, reflux ratio is continuously increased. Why? So that the product concentration, either it should be keep increasing, keep constant, keep decreasing, or none of the above. So the correct answer for this is that the reflux ratio increase in order to make the concentration of the product distillate to remain constant actually, because this is a variable reflux, not a constant reflux. So the variable reflux, the reflux ratio will varies according to the concentration of the distillate we want to connect at a constant concentration value. So if the reflux ratio is increased in the variable reflux, the product concentration remains constant. So suppose at one particular set of time, say T1, the reflux ratio is R1, and at that point the reflux concentration at the distillate is suppose C1. And when the passage of the time, say T equal to T2, the reflux ratio will be R2. We have increased from R1 to R2 because we have to keep the concentration of the distillate constant. Why? Because you want a constant purity product at a one particular concentration. That's why in variable reflux, the reflux ratio should be increased in order to keep the concentration remain constant. Okay. So these two MCQs relates each other. One relates with the constant reflux, and another with the variable reflux, and this has to be kept in mind while in solving the numericals also, and this is one set of the question that has been asked very time in the gate examinations also. So please go through this, both the one and the second MCQ. It's very important. You should take care of both these terms as well. So the third question, the Poisson-Savart method is a graphical method of the solution of. So like I already discussed, how this Poisson-Savart method is. Okay. So, yeah. So, like Machiavelli method, in what we consider as a constant molar overflow as an assumption, in Poisson-Savart method, there is no assumption related to the constant molar overflow. But however, we discussed that we consider as an assumption of energy enthalpies in terms of that, because we are going to do the energy balances, and there is no assumption for the constant molar overflow. So it's also a graphical method to determine the number of theoretical stages, which will do the enthalpies energy diagram, and each point on the diagram correspond to the concentration of gas and the liquid and a mixture of gas and the liquid involved in the separation process. So the Poisson-Savart method is actually a graphical method for the solution of both material and energy balance. So the correct answer is C, that is both or both, because we consider the energy enthalpy points in there. Now the Poisson-Savart method is more rigorous method than Machiavelli method, free from the assumption of constant molar overflow, suggested the use if the enthalpy of steam depends upon its completion or above. So this is the same point, like it's all of the above. It's free from the assumption of constant molar overflow, like we discussed. It's more rigorous, like like other than Machiavelli, and its enthalpy of the stream depends upon its composition. So we have already discussed these points for the Poisson-Savart method, and this can be asked in the final examination also. Please go through the basic concepts of this method also, as well as the Machiavelli and the variation in between these two. Variation in the sense the difference between these two methods. Okay, and the last MCQ that we are going to discuss today is that inside the distillation column, the pressure decreases gradually from top to bottom. So this is another set of MCQ that can be tricked in the final examinations. So just read it properly. So distillation column pressure varies gradually from top to bottom, bottom to top, and it depends on the type of the processes we are going to carry out, particularly in the industries. So in distillation column, pressure decreases gradually from top to the bottom of the column. Highest temperature is at the top of the column. Pressure increases gradually from the bottom to the top of the column, and temperature increases gradually from bottom to the top of the column. So this temperature and pressure plays an important role in the distillation column, and they both varies from top to bottom and bottom to top. But which varies particularly, and which is the correct answer here? So the correct answer here is the pressure decreases gradually from the bottom to the top of the column. Why? Because at the top of the column there will only be vapors, and the vapors are not can be compressed. Whereas in the bottom there will be a amount of the liquid. So the amount of liquid that has been pumped back in the form of through reboil in the form of vapor back to the rectifying section. So the pressure there will be much more higher compared to the top, where in which there will be only vapors which are going to be get condensed using a condenser and collected as a reflux drum, and a part of it has been refluxed back to the column in order to rectify the means order to increase the relative volatility or the increase the concentration or the purity of the more volatile components on the top. So inside the distillation column, the pressure decreases gradually from the bottom to the top of the column, whereas the temperature varies accordingly. So the correct answer is A. Similar question can be asked for the temperature also. So please go through all the basic concepts of the distillation columns. These two methods for determining, that is the Machiavelli and the Poisson-Savart method. There are assumptions in both the methods, variation and the difference between these two methods, and what kind of things we need to consider by solving these two methods for a number of the ideal stages for separation of the gas and the liquid. So this is what I have for today for you guys. So we discussed Poisson-Savart method and the multi-stage batch distillation with constant reflux, as well as we already seen. We have also seen what are the two various types of reflux, that is variable reflux and constant reflux, and how in the multi-stage batch distillation these two reflux will act accordingly. Plus we have seen Poisson-Savart method, another type of method for determining the number of theoretical stages for separating gas and the liquid, and how this method differs from the Machiavelli method. The only term is that it doesn't consider it's free from consumer overflow, and there is no like there is another energy balance, energy enthalpy balances for carrying out in the same case. So we'll be carrying out the energy balance as uh, in addition to the total overall material balance and the component balance. We're going to do the energy enthalpy balance also in this case for the constant subject matter, and we'll discuss some of the MCQs related to that. So we'll solve some of the numericals based on the basis of the constant salary next week, because today I have no numericals for that case, but I will already solve one numerical for the multi-stage batch distillation with constant reflux. So the next week is going to be the last week for this online live interaction also. So what I will suggest is that if any of you have any problem related to any of the week courses, sorry, any of the week lectures from week 0 to week 11 till week 11, like till today, please let me know in the next week, because next week is going to be the last week of this course, and then we'll be having the final examinations in the upcoming like October or the November first week. I don't know the examination dates. So it's better if you have any problems related to the assignments, tutorials, or some of the lecture notes, please let me know. So in the last week, that is the last week for this online live interaction, I can try to cover that up also. Meanwhile, we'll also cover the last week lecture notes and some of the numericals next week. So please go through the lecture notes once again. Next week is going to be the last for this live interaction for this mass transfer operation 1, and I think please go through all the lecture notes, numericals, assignments, what do you have the problems, please let us know. We'll try to cover up in the next week. Till then, we'll meet up next week. Thanks a lot. Goodbye.